Hello everyone, welcome back to Bytes of CEC. So in this lecture, we'll be talking about the gradient descent. Now what is a gradient descent? So gradient descent is a technique or a procedure which is used to find the maximum or minimum of a function. So what function are we talking about? So the function which we are talking about in this case is the error function. What is the error function? Error function is a function that computes the error made by the machine learning model. That is the difference between what the machine learning model has predicted versus what the true value was. So now what is a gradient? So gradient is a vector which is defined for any differentiable point of a function that points exactly towards the steepest ascent. So what we get from here is gradient is a vector, which means gradient will have two components to it. One is the direction of the steepest ascent and second is the magnitude. So now why do we use this term descent when we are talking about like when the gradient gives the steepest descent? So let us understand using this diagram. So say you are standing at this point in the hill. So if I draw an arrow in this direction, it will give you the position towards the highest point of the hill. Or in other words, we can say that this gives you the position towards the steepest ascent, right? Now, if I draw an arrow in the exact opposite direction to this, that is at this point, you will be directed towards this point, which is the lowest point of the hill. So now in gradient descent, see, when we are dealing with the error function, we definitely would like to minimize the function. So what we are doing here in gradient descent is we are going downhill in small steps from any starting point in a function. Say in this case we are standing here in a step size which is proportional to the norm of g. So what is this norm of g? So we are considering that say the gradient is depicted as g. Norm of g is, it is a function. Norm is a function which gives the magnitude of a vector. So the step size will be proportional to the magnitude of the original gradient. But what we are doing is we are moving in a direction which is just opposite to what the gradient is. So we are moving towards the negative gradient in this case. So far what we are talking about is we are just scratching on the surface. We are just keeping the discussion very surface level. But what is the basis? What is the mathematical basis of it? So the mathematical basis is given by the Taylor expansion series. So say if you have a function like which is say fx, so it will give you, like, consider a value h which is very small value. So it will give you, Taylor expansion series will approximate what would be the value of fx plus h. So fx plus h is given by fx plus h into, now this term means this is the differentiation of fx with respect to x. So dfx of dx, which is very similar to your dy dx. Only thing is, in case of dy, we are using dfx. So you can just substitute y with fx. So this is the first order differentiation that we say. Then h square by 2. This is the second order differentiation, that is d2fx dx2. This is the n minus 1th order differentiation, and this is the nth order differentiation. But don't get afraid, we are not going to deal with so many terms. What we are bothered about is just these first two terms, and the entire from here to here, it will be substituted by OH square. So now if I rewrite this Taylor expansion series, the approximation function looks like this. Fx plus h is given by fx plus h into f prime x, which as I said, dfx of dx, plus oh square. So we are replacing this as h square. Now what is this f prime x? Now this your f prime x is actually the gradient of the function fx with respect to a point x. Like if we consider a starting point x at that point. So now what we have done in gradient descent is we have moved in a direction which is opposite to f prime x, and as we said that we were moving with a step size proportional. So let's just start with a proportional factor. So any proportionality constant, say in this case proportional means, say if A is proportional to B, it means that A is equals to some K into B. So in this case our K we will be considering as eta. So eta is a very small number we'll be considering, which is greater than 0. And since we are moving in a direction which is opposite to a gradient, this is depicted as minus f prime x. So now we consider h, since we are moving, so this h is now replaced as minus eta into f prime x. Alright. So if we substitute the value of h as minus eta f prime x, we can rewrite the equation as this: x minus, we are considering the left hand side now, eta f prime x equals to fx. Fx is, it just remains same. Again we have h, so this part will be minus eta f prime x, and we have another f prime x, this one, into f prime x. So twice f prime x will give you the square root, the root over f prime x. So this is why the term looks like this: eta into f prime x for h into f prime x, which was already there. So this is going to look like this, and now this is also substituted. Now this minus eta f prime x, the whole square. Now if we choose a very small eta, we can ignore these higher order terms. This is going to have a very small value which can be easily neglected. So now if we just consider this part, see, eta we have considered that to be greater than 0, and now we are taking square of f prime x. So this is also going to be greater than 0. So we can say that we are subtracting some value from this function fx. So in other words, we can say that fx minus eta f prime x is almost equivalent to less than fx, because some factor is getting subtracted from fx. So if we move in that direction of minus eta f prime x, the value of the function is actually decreasing. Now in other words, we can say that if we update the value of x as x minus eta f prime x, the value of the function will be decreasing. I hope I have made my point clear. If we update, we won't consider that if x minus eta f prime x is less than x. We are not considered with x in this case. We are bothered about the error function. We are trying to decrease the error function, right? This is what we are trying to decrease. So we are going to update x in a way so that the value of the function decreases. So if we update the value of x as x minus eta f prime x, the value of the function fx is going to decrease. So now if we look at the steps, we'll be seeing that the first step is going to be selection. So in selection, what we are doing is we are choosing a minimum value for f prime x. That is the minimum value of the gradient, and we call that as E. We will also be choosing a value for maximum number of iterations, like how many times we'll be updating the value of this x. So why do we need these two? I'll be making it clear in a few moments. And then we have to choose a starting point, which is x, and we also have to choose eta. The next step is going to be loop and update, where we will be updating the value of x as x minus eta f prime x, and we'll be also be computing the value of fx. Now the third part is going to be the stopping criteria check, like how far we will be continuing with this particular section, like how many times we'll need to update the value of x. So the first condition checking will be if the value of f prime x is less than e. E was the minimum value of f prime x. If it goes below that minimum value, if it is yes, that it has gone below the minimum value, we will be immediately stopping the algorithm. But if we say that no, it is still equals to or greater than e, we will be checking another criteria, which is if the number of iterations is equivalent to n, which was the maximum value for the iteration number. If it says that yes, the maximum value of the maximum iteration number has been reached, we will again stop the entire like the gradient descent, this procedure. But if we say no, we will loop again. That is, we will update again. So for each iteration, we need to check. Now the question is, if we already have this condition that f prime x is less than e, why do we need this condition? Why do we need both the conditions? It could have been like number of iterations, or it could have been the after this particular, if it goes below this, the gradient value goes below e, we are going to stop the entire thing. But there is a like a reason for doing that. Say your value of e is say 0.0005. Oh, before explaining this, let me explain that why do we need to check this, that if it has gone below a particular point. Say if your gradient value is say 10 to the power minus 15, and you have a very small eta value, then this factor will be almost very close to 0. So what happens here is, actually your value x is not getting updated, it is remaining almost the same. Like, since this is almost equivalent to 0, and now if you don't like keep this as a stopping criteria, it is going to loop on forever, because your fx value is not going to decrease, and you are just looping it for infinity. And now the question is, why do we consider this as another stopping criteria? Say you have a gradient value, like if you choose a value of e as say 0.005. Now your gradient value for say past few iterations has been 0.006. So essentially this condition will always fail. Like this is always greater than this value e, but the effective value of minus eta f prime x is also not moving in a direction that you are desiring for. Like this is also a very like 0.005 and 0.006 is not going to make much of a difference. So in that case, your function is also like decreasing in, like your error function is almost remaining the same. It is not updating very fast, or the solution isn't converging very fast. So instead of just making it loop forever, we are also checking that, say after 500 iterations, let's stop it. So we are not going to consume a lot of resources for your gradient optimization. So for that reason, we have both the criteria. So basically, in the loop, in the actual algorithm, this is an OR criteria. So is f prime x less than e, or if number of iterations equals to n. This is how it is implemented in our gradient optimization algorithm. Now, so far we are considering only one feature, that is x. So x here is actually the feature. So in our real world problem, we will not consider or we seldom will come across a problem which has only one feature. So we in almost all the problems actually, we'll be dealing with a d-dimensional feature vector, which is there will be around d, say, features in your trading problem. So what do we do that? So we were considering f prime x, which was like dfx with respect to that feature vector. So with that single feature. So what about the feature vector? If we consider this feature vector, so what changes we'll be doing is, we will be considering another vector. Now this operator is known as the Nabla operator, NABLA. So this is going to be your gradient, which is computed as, this is a partial differentiation, that is, we differentiate fx with respect to first feature, that is x1. Then the second element in this vector will be del fx with respect to del x2, which is a second feature, and it goes on like this, and we'll be considering at last it's del fx with respect to the last feature. So we will be considering another matrix. We need to compute this matrix, with which will be finding the partial differentiation, where each element is a partial differentiation with respect to that partial differentiation of the function with respect to that element, x1, x2, and finally xg. And say your age in this case is epsilon, it's all the same. So this is how the equation is going to look like. So we'll be considering the the transpose of epsilon into the Nabla of this, and this is the higher order term which we generally kind of ignore. And your x value is going to be updated in this fashion. So x minus eta. So eta is going to be a scalar. This is not a vector, this is a scalar, just like the previous one-dimensional problem. And that will be multiplied with this vector, Nabla of fx, which is the gradient of the feature vector. So this is the change for a d-dimensional feature vector. It's essentially everything is the same. Only thing we are dealing with vector, and we'll be considering these necessary changes in this particular equation. So now, how good is a gradient descent optimization? Say your error, if I graphically plot, your error looks somewhat like this. This is how your error looks like. And now you are starting from this point. This is your starting point, say. Now naturally you will be directed towards this point. Now, at this point, when the function tries to reach at this point, it will be seen that the function is increasing. But our intention is to minimize the function. So now your gradient descent might, or actually will be, like returning this value as the minimum point of the error function. Now, when we know that this is the actual minimum point, so this is known as the local minima. So instead of returning the true minimum, the value of the function, it might return a suboptimal solution in this case. So there are two minima. So this is where the value of the function decreases, but this is just a local minima. This is also a minima, and this is the point where your error function is, or the error is at minimum. So this point is known as the global minima, and this is the local minima. So if you consider only this point, so at this point this is also a local minima, and this is also a local minima, but this is also a global minima. So every global minima is also a local minima, but every local minima is not always a global minima. So if your starting point was such that it gets stuck in a local minima which is not a global minima, then it may return a suboptimal solution. Now, this is a problem with almost all the optimization problem in case of deep learning, because they do get stuck at local minima and they will return you that value. So it is not actually so bad, but of course this happens, and you need to know the actual thing that a problem like this might happen. Now say you have started your search from here. Search for the minimum value starts from here. Forget about this case. This case is done. Now you start searching from this point. Now at this point, the gradient value will be very less, and the progress of the function is going to be very low. And at a very extreme cases, it might be the gradient becomes totally zero and the optimization problem practically stops, because there has been no changes to the value of fx. So that condition that it becomes less than the minimum value, that becomes less than e. Remember the algorithm that we were discussing. So this is known as a flat plateau, and this makes the training process slow. So it might be that maybe if it is greater than the gradient, the minimum value of the gradient that has been selected, it might be that your maximum number of iterations is reached and the problem just halts. So anyways, this is going to make the training process very slow, an error surface like this. Now say your search starts from this point that is very close to the global minima. Now at this point, the value of gradient is pretty high, and say your learning rate is also on the higher side. So the step size is going to increase a lot. Say this is your step size. So now you're reaching here, you're falling very fast, and since your step size is fixed, instead of hitting at this point, you end up at this point. So you just have missed this point because the step size was such that after this point you will be reaching this point, considering the step size instead of this. So this is also another problem. This is known as diverging. So instead of converging, you have just diverged from the true minimum value. So a large value of eta might cause the solution to diverge. So these are the problems with a gradient descent optimization, but anyways it is very helpful for back propagation of error during your training process. So that is all about gradient descent. I will be making another video on how to choose the proper value of eta, but I'm not covering it this time. So that was all for today. So thank you for watching.